matrix and we want to reorder rows and columns in such a way you get this. So suppose we have symmetric case for simplicity. So it means we have a group of variables and they have certain submatrix corresponding to this group of variables here, second group of variables, but we demand that this block is 0. We demand that this block is 0, it means these vertices, if we look for the graph of these variables, they are not connected to this. So there is no connection. So if we associate with our sparse matrix a graph, then it means these are two sets of vertices which do not have an edge. Okay? And this, but of course, if the graph does not have any disconnected components, this is not possible. So you have to have this third group of variables, which is called separator, in such a way that this third group is connected to the first group, third group is connected to itself, the third group is connected to the second group, but the first and the second, they are not connected. So I'll show you how to do it using a graph. It's really very simple, in terms for simple graphs, of course. But if we have the structure, then we just generalize the LU factorization using block operations. So we do block LU decomposition, and this is how it will look like. So we have this block triangle factor here, and if you want to do this recursively, we will just do the same with this block and this block. And you will have this sort of nasty formula. This is called so-called Schur complement, and you will have this Schur complement in the homework, or maybe you already have, I don't remember, but it will be somewhere in the homework. This is, again, sometimes the names, things have similar names. So Schur decomposition or Schur complement, they are absolutely different. So the only common is the guy who proposed them, and maybe he didn't even propose them. These things only have his name on it. If you know the Arnold principle that things are never named after the inventors, which also applies to Arnold principle as well. So this is probably, yeah, I have heard stories, but not so important. So basically, you do block elimination. You have to be very careful about the ordering of the product, because matrix by matrix product is not commutative here, so we have to assume that this block is invertible, this block is invertible. So for example, if you have positive definite matrices, this is always the case. These are just minors which are invertible. So you have to compute the inverse of this guy times this. So what we want that this third group of variables is small. So we want to find the minimal separator between those. So we hope that this is a very tall matrix. Well, ideally, if we remove just one vertex and the graph becomes disconnected, that would be, in this extreme case, that would be just a column, and this would be just rows. So what it means then, this product, we need to solve a linear system with this block with some number of columns. And this number of columns is assumed to be small. So, and this would be a recursive algorithm later on. So if we already have factorized in a sparse way this block, then solving linear system with few right-hand sides is quite easy. The same here. So we will need to compute this block. This block will be the size of n3 times n3. And we hope this would be small, but this would be a dense matrix. Nothing can be done about that. This would be a small, dense block. But we hope that the separate part is small. Here, and the same is here. So if you know how to solve linear system with these large blocks, we will need to compute the small block and store it. This is Schur complement. This is a block diagonal matrix. So we reduce the problem to solving some linear systems with these blocks. This is and then, of course, how we find the permutation. But again, the key thing is that we need to make this block smaller, and we want to have in such a way that we have zeros between these two. So this should be large, this should be small, and this here we should have zeros. Okay. So this is all related to graph. So first, let's illustrate on the two simplest examples, arrowhead here and arrowhead here. So, and the graphs have the following form, we just change the numbering. But if we eliminate here 4, this would be our separator. The third group of variables will be just the vertex with number 4. Then the graph is split into 3 disconnected components, and we get what we want. If we remove, but if we remove 1 in this block, you will still have 1 connected component. And that's what we already introduced. So we have a separator in the graph. So a separator, you have a graph, and the graph, just again say that the connection between the sparse matrix and the graph is very simple. So we just take, without values, we only look at whether the element is 0 or not. And we have that the graph with the adjacency matrix given by the sparse matrix. So from the graph we can construct the adjacency matrix. From a sparse matrix we can construct the graph. So a separate story of how we can include weights. But if we're talking about fast direct methods, the weights are not important. Yeah, we are only talking about zeros and non-zeros. So given if we start from a sparse matrix, we just take a sparse matrix and construct a graph. And then in this graph, we define a set of vertices. And if we remove these vertices, well, we have at least two components. And if you construct such a separator, then you basically have the ordering, but simple, much simple to see from the picture. Okay, wait, what's going on? And for the Laplacian, but Laplacian corresponds to a very regular graph. So the graph can be visualized as a two-dimensional grid, and the nodes are connected to the nearest neighbors, and that's what happens with this matrix. So if you take this matrix, the graph looks like this. And what you can do, you can take out a line. That would be the third group of variables, sigma, for example, 3 in the previous. And then these two components will be disconnected. So if you have, for example, 500 times 500 grid, we have to remove 500 points. And that would be, of course, the minimal separator. We remove 500 points, and we are left with two disconnected components approximately of the same size. And we cannot, again, obviously, we cannot take out smaller components. So what we will have in this case, we will have this block. Where is it? So if you have, for example, 500 times 500, this would be 500 times 500 matrix, dense matrix. So that's not too much, right? The full matrix is 500 squared times 500 squared. So this is hundreds of thousands. And this is only 500 times 500, and we can afford to store it. But still, the size of this matrix grows. It's for the square root of n, and the complexity would be square root of n to the cube, because we have to do dense matrix by matrix operations. So you will get this additional square root of n factor for factorization. Okay. Something else here? Yeah. And after this permutation, if you take exactly, so inside this, we permute the vertices in arbitrary order. Then we take these variables in arbitrary order and the separated in arbitrary order, and exactly we will have the block arrowhead structure. So we get this kind of structure after such permutation. But then, of course, we will need to do this procedure recursively. So we will need to split the vertices corresponding to the component named alpha into two halves using another separator. This would induce another permutation, and so on. So constructing, if you know how to construct the separator, this automatically induces the permutation of unknowns. So we split, then we split, this is another permutation, and again this hierarchical structure is uniquely defined by two things, the permutation of unknowns and the number of points in each component. Okay, so then the construction of permutation is reduced to the problem of finding a separator. So if the graph has a simple structure, so it's a two-dimensional grid, then you can, just by looking at this, you can find the optimal separator, right? You take it in the middle. But suppose the graph is somewhat arbitrary, you only know adjacency matrix. The question is how to construct a separator. There's a lot of methods for doing that. If the graph comes from some geometrical problem, these are some nearest neighbors in three-dimensional space, then you can use geometric methods. So for example, you use such structures as quad trees, KT trees, inertial bisection, and so on. So you know that you have a point cloud, then you, for example, find the center of mass of this point cloud and put a plane through the center of mass. So you can construct separate. If you know this, if you have this additional information about the geometry of the original problem, then constructing a separator is an easy task, more or less, not so difficult. But if you only have the graph, this is not an easy task, and there are many methods for doing that. And in details, we will discuss one, so-called spectral clustering. There are packages that do nested dissection. Well, you can look, that we developed for many years. MOOPS, Pardisa, OMF-PAC. They have interface, so some of them they power Python. The codes, well, since this is a big package, it's very difficult to follow. Again, if you do not have to do anything in the evening, you can look at user guides of these packages. And this is like old school Fortran code, very difficult to follow. Yeah, but it works. So what should we do? Probably rewriting it from scratch will not save a lot. So this is implemented. So that's the summary of the nested dissection. So what you need to do, you need to find the separator of the graph. Then you have applied this in divide and conquer manner, split it into half, factorize, find the permutation, and so on. So I know of some in-house codes that work very well, but like the ones that I know online, that they lose to other algorithms, but they are not so simple to explain. And in the second part of the first half of the lecture, we'll talk about computing separators. So it's not a trivial task. Computing a separator of the graph is not a trivial task. Still, it's an active area of research. Still, papers are being published. Yeah, so geometric method I already told you. And if you just have a matrix, one of the good methods is so-called spectral partitioning. Well, spectral partitioning is a nice story. So there are many other methods, which we are not going to discuss, but there are references if you want. This doesn't look like an active area of research. These are classical algorithms, but actually, well, the existing approaches, they are quite complicated and contain a lot of heuristics. So, in my opinion, this is more heuristics adapted to particular classes of problem rather than some fundamental results, but I might be wrong. And spectral partitioning is a very nice, it actually works quite well. Yeah, so again, the details you can look. Let's talk about spectral graph partitioning, which this is one of the applications of computing eigenvalues of large sparse matrices. So the guy who proposed it was this Miroslav Figner, Czech mathematician who died maybe 2 or 3 years ago. He proposed a huge number of things in numerical analysis and linear algebra. Yeah, absolutely great guy. Well, yeah, I met him several times, but he was already 80 something. But he was, and this was one of his proposals, one of his results. And also, this is an example of the eigenvector, which has the name, it's called filter vector. So the idea, what is our task? So the task is that we need to split our vertices into two groups, group 1 and group 2, in such a way that they are separated. So we do that by assigning plus and minus 1. So group 1 gets +1, group -1 gets -1, and we want to minimize the number of connections, the number of edges going from group 1 to group 2. Right? And formally this can be written in terms of this functional. So we minimize xi minus xj, and we sum over all the neighbors. So this would be larger than 0 only if I and j belong to two different clusters. If they belong to two different clusters, this would be non-zero, and that's what we want to penalize. We want to penalize the number of connections between these two groups.